So ionic compound naming, they follow a certain set of rules, considering that it is an ionic compound. So first of all, we have to know, what is an ionic compound? An ionic compound is any chemical compound between a metal and a non-metal. A metal and a non-metal. Okay, so any sort of compound that contains both a metal and a non-metal would be considered an ionic compound. Okay, ionic compound. So let's review on your periodic table. Why don't you go ahead and get out your periodic table real quick. You've got a periodic table that's double-sided, and it includes the periodic table of ions. That's really kind of what we're going to shift our focus to. How many of the metals sit on the left to that? What do we call that little squiggly line we drew? Do you remember? Did you draw that little dark line? Yeah. Okay, I call that line the stair step, okay, because it looks like a set of stairs. Okay, so left of the stair steps is metals. Right of the stair steps are nonmetals. Okay? If you look at the periodic table of ions side of yours, that's the one that has all the charges, right? What's the charge on all the metals? What are the charges of all the metals? Positive. And what do we call a positively charged ion? A cation. Okay? So there's a couple different ways you can think about ionic compounds. You can think about them either being between a metal and a nonmetal, which is true, or between a cation and an anion, also true. Okay? Yeah, they're positive. That's right. Okay? So cation and an anion. Cations are the positive and anions are the negative. All right, I want to look at one other thing here on your periodic table. Let's review here our valence electron patterns. Do you remember what a valence electron is? Yes, it's the outermost electrons. How many valence electrons do the group 15 group 5 nitrogens group? How many valence electrons do they have? 5, right? They follow their group numbers. So if we're talking about group 1, hydrogen, lithium, sodium, all of those, they have 1 valence electron. Beryllium's group has 2. We skip over to boron's group. They have 3. Carbon's group 4. Nitrogen 5, 6, 7, all the way to 8. You remember how we labeled the periodic table with our group numbers? And they follow that count of valence electrons. Okay, so stay with me here. I want you to figure out where these charges are coming from. What's the charge on all of the elements in group 1? Positive, and if there's no number there, we know it's a 1, right? So all of the group 1 elements have a charge of plus 1. Okay, so the group 1 elements have a charge of plus 1. How many valence electrons do the group 1 elements have? They have 1 valence electron. So let's talk theory here for just a second. If I want to have 8 electrons, that's my goal, right? An atom's full goal is to have 8 total electrons in their outer shell. But these group 1 elements only have 1 electron in their outer shell. They've got 8 of them in the shell underneath, but their outermost shell only has 1. So is it easier for sodium, lithium, potassium, is it easier for them to gather in 7 electrons, so they have 8 total, or is it easier for them to give away their outer shell electrons, so they've got 8 on the shell underneath? Give away 1. So if sodium gives away 1 electron, what charge does that leave it with? A plus 1, right? Okay, so I want to walk through that again because I'm not sure that we're all grasping what I'm talking about here. So let's look at sodium. Here's a basic elemental picture of sodium here. Here's sodium's nucleus. The first shell has 2 electrons, 1s2. Second shell has 1, 2, 3, 4, 5, 6, 7, 8. Okay, 2s2, 2p6. There's your 8 electrons. They don't look like this, but I just want you to have a picture of what's going on, okay? So far, sodium's got 10 electrons, but it's supposed to have 11, right? A neutral sodium atom would have 11 electrons. We agree with that? Yeah. Okay, so if our goal is to have 8 electrons, we said it's easier to give away 1 than to gather in 7 more to fill up that shell, right? That would take too much. So if it gives away that 1 electron, now it has a shell, an outermost shell that has 8, which is what it wants. So it started with 11 electrons. It gave away 1, which means now it has 10. If it has 11 protons and 10 electrons, that means the charge is +1, right? That's where these charges come from, okay? That's it. They're not arbitrary. They come from the fact that sodium wants to give away that 1 electron, and that would leave it with a +1 charge. So if you look at group 2, they all have 2 valence electrons. So is it easier for them to give away their 2 or to gather in 6? Give away 2, and that leaves them with a +2 charge. Okay, flip over here to fluorine's group, the halogens group. What's all their charges? -1, right? -1. So fluorine, chlorine, bromine, iodide, they have 7 valence electrons. So is it easier for them to give away 7 or to bring in an extra one? Bring in an extra one. And if it collects an extra electron, what charge does that leave it with? -1. Okay, very good. I just wanted you to kind of see that really quick before we kind of got started on it. But let's get into our naming rules. We're going to start with what are called monatomic ions. What do you think that might mean? What's mono mean? 1. So a monatomic ion is just an ion that's got a single atom, like just a regular ion. Okay? And the way we name monatomic ions follows this rule. A cation, they keep their regular name. Okay, so if we had this, calcium +2, it's still just called calcium, right? It doesn't get a name change just because it has a positive charge. So the cations keep their regular name. Doesn't matter the charge. Nope, and doesn't matter the element. And you'll see that if you look on your periodic table of ions side, all of the positively charged ones still have their regular name written there. Do you see that? Okay. But an anion, they take their ending and they end in IDE. So this IDE ending tells me I'm dealing with the negatively charged version of that atom. So if it was O -2, it would be called oxide, not oxygen. Okay, and if you look on your periodic table of ions, it does have them all written as "ide." Okay, so the single type of atom that's got a charge, if it's a negative charge, it's going to end in IDE. Do you see that difference there, right? We're going to really be working on this ions side of our periodic table. So do you see how all of the anions here, their written names ends in IDE? Phosphide, nitride, sulfide, all that. That's because we're dealing with the negatively charged version of that. Okay? Very simple in terms of monatomic ions. So we don't really need to do a whole lot with that because you're always going to have access to this table. This is going to be something that you'll be able to use on tests. It's not like I need you to memorize all of that. Okay, let's move on to something called binary. Actually, no, I want to do one more thing. Let's look at polyatomic ions. What do you think poly means?
Many.
It means many. So polyatomic ions are just ions with multiple atoms. Ions with multiple atoms. And what does it mean, first of all, to be an ion? Right, if I say it's an ion, not just a compound, it's an ion with multiple atoms. What's that mean? It has a charge, right? An ion is anything that has a charge. So polyatomic ions are ions that have multiple atoms. Up at the top here in this box, you will find a table of polyatomic ions. And they usually have an ending of ate or ite. They have a different type of ending. Those are things that up here in this box you will need to reference, but we won't have to memorize those. Okay, so that box of polyatomic ions is up there at the top. Here's a couple examples. PO4, that compound has a charge of -3 and it's called phosphate. PO3 -3 is called phosphite. But if I just had P -3, what would I call that? Right, these are two polyatomic ions. This is a monatomic ion because it's just one type. So what would I call this one? Phosphide. Good. It just ends in IDE. Okay, so you see how these are all different things, right? They all have different identities. They all have different names. They all behave differently, right? This one is PO4. This one is PO3, and this one's just P. Okay, are we seeing where that's coming from? Phosphate and phosphite I just got from our table. Actually, phosphite's not on the table, but phosphate is. Okay? All right, let's get into the actual naming rules. So we use monatomic ions and polyatomic ions to help us build compounds. Okay, so let's look at an actual set of rules here. We're going to start with binary ionic compounds. Okay, what do you think binary means? Between how many? Yep, these are compounds between two types of atoms. Okay, binary ionic compounds are between two types. Okay, the rule for binary ionic compounds, when we build ionic compounds and when we contain ionic compounds, the rule is that the overall compound, actually I don't want to say overall, the compound must be neutral. Okay, the compound must have an overall neutral charge. So what numerical value means neutral? Must have an overall charge of 0, okay? Needs to have an overall charge of 0. So that means if I put together, just think through this with me. If I put together a cation that has a +1 charge and an anion that has a -1 charge, will they fit together perfectly? 1 to 1? Yeah. Okay. If I put together a cation that has a +2 charge and an anion that has a -1 charge, how many of those anions do I need to put in there? 2 of them. If I have a -1 and a +2, I'm going to have to put 2 of those anions together. Okay, that's what we're going to start looking at, is what is the ratio in which these elements need to fit together. Okay, let's start with one here. We're going to start with building the formula for magnesium bromide. Magnesium bromide. Okay, the written name is always just written cation, then anion. That's it. Okay, the cation comes first and the anion comes second. So I want you to look on your periodic table and I want you to find magnesium and I want you to find bromide and just write them out individually with their charges. Figure out what the charge for both magnesium and for bromide is. How are these two going to fit together to make my overall charge be equal to 0? Will they go, if I put them together just like this, M, G, B, R, would my overall charge be equal to 0? No, because I have a +2 and a -1. So how can I adjust that to make it neutral? Do I need more of the positive charge or more of the negative charge? Okay, so if I add another bromine, does that make me neutral? Yeah, so the way I would write this final compound is MgBr2, right? This down here is called a subscript, and that subscript tells us how many of that atom we need, right? We know about subscripts because we did molar mass and all this stuff like that, right? We know that means how many of those atoms do we need. So this would be a neutral charge. So this would be the actual formula for magnesium bromide. Okay, do we kind of see how that works? They just have to fit together so that they are neutral. Okay. Let's try another one. Let's try sodium nitride. Sodium nitride. Okay, sodium is Na and it has what charge? +1. Nitride, IDE, means it's just looking at the regular nitrogen right here. Nitrogen or nitride has a charge of -3. So do we think those are going to fit together right away? Not really, right? So are we going to need more positives or more negatives? Or positives. So if I bring in another sodium, does that work? Nope, I'm going to have to bring in one more. And so that means that would be Na3N. Do we feel okay with that? Okay, and the way we write our written name for it is just writing the name of the cation, then the anion. It's important for us when we do ionic compounds, the positive always comes first. When we build any sort of chemical formula, we work left to right on the periodic table. So whatever element is furthest left needs to come first in our formula. Okay? All right, let's try calcium oxide. Calcium oxide. Calcium is Ca, and it has a charge of +2. Oxide is just O, and it has a -2. So are those going to fit together right away?
Yeah.
Yes, right? There's nothing else that we need to do in terms of adding any more positives or negatives, so it just becomes CaO.